Welcome back to another video, grade 12s. In this video, we continue with the multiple choice section of the paper. We're going to look specifically at question 1.4 to 1.6. Question 1.4 says a ball is dropped from a height above a floor. If it is dropped, it means that its initial velocity is 0 meters per second. Now on the right hand side of your screen, you can see that I have drawn an image to help us with this, with analyzing what is going on. And based on what we just read, we know that the initial velocity of the ball is going to be 0. This ball is dropped and it therefore becomes an object in free fall, because later they say that we must ignore air resistance. So the only force acting on this object is the gravitational force. They then say the ball makes an elastic collision with the floor at time t0 and it bounces vertically upwards. So what is going to happen is that this ball is going to drop and then it is going to hit the ground with what I'm going to call its maximum velocity. It is going to collide with the ground. So a collision takes place. But after the collision, since this is an elastic collision, the kinetic energy of the ball is conserved. It remains constant. And therefore, this ball is going to leave with exactly the same velocity. It's going to bounce upwards with exactly the same velocity with which it hit the ground. The ball will then move up to its maximum height, with the only force acting on it being Fg. And when it reaches its maximum height, its final velocity is once again going to be 0. They say, ignore air resistance. Which one of the following graphs shows how the total mechanical energy of the ball changes with time? You're going to notice in all of these graphs, right, that the graphs are different, but if we look at answer A, C, and D, the mechanical energy is changing. Graph B is, however, special because graph B has that the mechanical energy stays constant with time. Now, what is mechanical energy, grade 12s? Mechanical energy is the sum of the potential energy and kinetic energy of an object. And whenever you see the words mechanical energy, you should remember the principle of conservation of mechanical energy, which says that in an isolated system, the total mechanical energy remains constant. And we say that an isolated system is one where the net external force, excluding the gravitational force, is 0. So if we look at what happens before the collision, during the collision, and after the collision, we can question whether or not the mechanical energy is conserved. Are there any external forces acting on the system? In the beginning, when the ball is dropped and falls down, the only force that acts on it is the gravitational force. So we expect that the mechanical energy right at the top is equal to the mechanical energy anywhere in between and is equal to the mechanical energy that the ball is going to have when it just reaches the ground. The ball then collides with the floor, so the net external force is no longer 0. But it's going to leave the floor with exactly the same velocity, or the same, not velocity, sorry guys, it's the magnitude of the velocity is going to be the same. It is now just upwards. So when the ball travels up into the air, we know that the only force that is going to act on it is once again Fg, the gravitational force. So we expect that the mechanical energy of the of the ball after the collision is equal to it in between as it moves upwards, and that is equal to the mechanical energy when the ball reaches its maximum height. The only graph that shows conservation of mechanical energy for this specific system is graph B. The mechanical energy before time t0 is constant and the mechanical energy after time t0 is constant. Therefore, the answer to question 1.4 is B. Question 1.5 says, consider the two spectrum diagrams below. We have diagram number 1 and diagram number 2. If we look at both diagrams, we can see on the left-hand side the word blue, and on the right-hand side we see the word red. Now they say diagram 1 represents the spectrum of an element in a laboratory on Earth. Diagram 2 represents the spectrum of the same element from a distant star observed from Earth. Which one of the following can be deduced from the spectra above? The star is moving towards Earth. It is at rest relative to Earth. The star is moving away from Earth. Or both the star and the Earth are moving towards each other. Now, when we look at an element in a laboratory, its velocity is going to be 0. So it's going to be at rest. If the distant star is not moving, then we expect no shift in the spectrum. If it is moving, however, then the spectrum is going to either be blue or red shifted. Remember, a blue shift implies that it is moving, the star is moving towards us. A red shift implies that the star is moving away from us. So let's now analyze the diagrams given to us to determine whether or not the star is at rest or moving. If we look at diagram number 1, here is the first line that we see. This is shifted towards the red end of the spectrum. If we look at this line over there, it is also shifted towards the red side of the spectrum. And over here as well, we see a red shift. It is moving, so all of the lines in the spectrum are moving towards the red side. Therefore, grade 12s, we can come to the conclusion that this is a red shift, and therefore the correct answer to this question is question C. The star is moving away from the Earth. If there was no shift, then B would be the correct answer, because it would mean the star is at rest. If it moved towards the blue side, if the spectrum moved towards the blue end, then we could go with A or D. But the correct answer here is C. We're now on question 1.6, which is the last question in this video, and it says, the diagram shows the field lines for the combined electric field due to two small charged spheres, P and Q. Which one of the following combinations below shows the polarity of the spheres P and Q? Polarity basically speaks of whether or not the spheres are positively charged or negatively charged. That is what we are speaking about when we use the term polarity in this section. Now remember, when we speak about the direction of an electric field, we say that an electric field, the direction of an electric field at a point, is the direction in which a positive test charge would move. Therefore, electric field lines are going to point away from a positively charged object, and they are going to point towards a negatively charged object. So if we look at the field lines in the diagram, we see that the field lines are all pointing away from sphere P. That implies that sphere P is positively charged. If we look at sphere Q, we see that the field lines are all pointing towards sphere Q. Therefore, sphere Q is negatively charged. Now we look at the options. Let's start off just by looking at sphere P so that we don't make any silly mistakes. Sphere P is positively charged, so we know either option C or D is correct, and we highlight those options. Now we go on to sphere Q. We know that sphere Q is negatively charged. When we look at the options C and D, the one that says sphere Q is negatively charged is option D. Therefore, the correct answer to this question is D. Grade 12, this brings us to the end of this video. In the next video, we're going to finish off this multiple choice section in the 2021 question paper.